All right, Calc AB, Unit 4, Day 1, assignment, office hours. If you didn't catch it, I changed the assignment a bit, cut out about half the problems. Should have checked your odds in the back of your book, which almost all these were, except for 28. And I'm going to go ahead and go over these problems now. So these first problems said, assume that all of the significant features of the indicated function, including its end behavior, can be correctly surmised from the graph shown in the figure. Number one, for the function f graphed in the accompanying figure, find a bunch of different limits. So I'm going to go ahead and draw the graph real quick, which I think wouldn't be a bad idea for you to do. I did cut down the assignment by half, so maybe that would allow you to do a better job. Okay, so there is looks like a solid dot here at 1, open dot at 3, and then open dot at -1 down here. And then the graph goes like this. And the graph goes like this. Looks like horizontal lines. So, based off this graph, part A says limit as x approaches 3 from superscript negative. That means from the left, one side limit. So as we approach 3 from the left, it equals -1. So it'd be good to go and just write down the problems. It's not a whole lot of work to show on these. And we're doing from the right side, which would be 3. And then part C, we're doing the overall limit. As x approaches 3, that means both sides. And that does not exist because they don't agree. And then D is the value of the function at 3, which is totally independent of the limit, which is 1. So there you go. So that's what we're doing. Number 3, the graph looks like it maybe crosses around, or I don't know, there's a kind of a significant dot at 4. Graph kind of goes like this, and it kind of bends upwards. So something like that. So part A says limit as x approaches 4 from the left. This is 4 right here. So from the left, it appears to be f of x. Looks like it's going towards 1. And B, limit as x approaches 4 superscript plus, which means from the right side, appears to also be going to 1. So the overall limit, which includes both sides, and since they agree, the answer is 1. And D, the value of the function of 4, which doesn't have to agree with the limits, actually does, which will be true if it's a continuous function. Okay, number 5. Draw a sketch. So kind of looks like a absolute value graph. That's an open dot. So something like that. So A says the limit as x approaches -2 superscript negative of capital F of x, which is what they just call this function. So we're approaching -2 from the left, and it approaches 0. And then limit as x approaches -2 from the right. Oh, no. Yeah, let's see. Yeah. Very predictably is also 0. And part C, the limit as x approaches -2. Well, they agree, so it's going to be what they both are, 0. D is the value of the function at -2, which is actually 3. There's a jump. And then E, the limit as x goes to -infinity of f of x. Well, -infinity means we're going up this way, and it looks to blow up. Now, technically, we would say does not exist, but I want you to go ahead and write positive -infinity. It's going to some kind of infinity. It's in behavior, by the way. F, when you go to positive infinity, it goes to positive infinity. So that's what we're looking for. Okay. 7, try and sketch this graph. So this graph kind of goes like this. Looks like it's going towards this horizontal and vertical asymptote. And then over here, it crosses that horizontal asymptote and then looks like maybe it's going towards y equals 0 asymptote. Maybe something like that. Okay, so A is the limit as x approaches -2 negative, and they're using this Greek symbol that's theta. So as we approach -2 from the left side, this dives to -infinity. Technically does not exist, but that's what I want you to write, and I think even the book has that answer in the back. I will disagree with the book on some answers, and I'll tell you when. From the right side, it's going to positive infinity. The overall limit does not exist. Even if both sides were going to infinity, positive or negative, I would say does not exist. But they are clearly doing totally different things there. D, the value of the function at -2 is undefined, doesn't have a value, right? Division by 0 is probably happening. E, the limit as x goes to -infinity, so this is in behavior. So to the left, it looks like it's going to 2, right, towards that horizontal asymptote, y equals 2. And for F, it looks like it's going to 0. Looks like it's going towards the y-axis, or the x-axis, which is y equals 0. So there you go. We got a couple more of these. 9. So there's a function here. Sketch it. Okay, so this graph kind of looks like it's going like that. And over here, looks like it's kind of going like this. Maybe like it's going towards asymptote, horizontal. And then over here, it's going like this. Okay, so A says limit as x approaches 3 superscript negative. It means we're approaching 3 from the left side because negative infinity. B, probably predictably, approach 3 from the right side, which is also negative infinity. It's going down. C, probably the overall limit. Now, I think the book may have actually put negative infinity. I don't want that answer here. We really shouldn't do it for two-sided if they're both going infinity. They might even be going the same infinity at the same rate. I think that's what the book has. We want does not exist. I don't want infinity for a two-sided limit. D, the value of the function at 3 is not undefined. It's 1. There's a hole there. E, limit as x goes to negative infinity of f of x. I guess I didn't draw my picture good enough, but I guess it's going towards 1. Maybe it was better in the book. And then over here, I guess it's going to 2. I mean, my picture, maybe in the book it's better. So I mean, don't worry too much about those. Okay, 11. Got a graph. Okay. So the graph looks kind of like a sine curve, right? Kind of looks like something like that. It looks like it keeps going. It's like the amplitude is 2. I think that, these are nicer values. Okay. So A says limit as x approaches 0 from the left of capital GX, which is what they're calling this. So 0 from the left is 0. Zero from the right is 0. Two-sided limit as approach 0 is 0 because they both agree. D, the value of the function at 0 is 0 because it's continuous. And then in behavior of g of x does not go towards some specific value, so we're going to just say does not exist. And same thing for the in behavior on the right side. It bumps back and forth between -2 and +2. All right. Thirteen is a little different kind of question. It says, consider the function g graphed in the accompanying figure. For what values of x not x sub 0 does the limit exist? For what values does the limit exist? So, quick sketch of this graph. I think I messed that up. So let's see, that goes up to 4. And there's another here, and it goes down. Assume forever. Okay, so where does the limit exist? The limit of g of x as x goes to x naught. Where does it exist? For what values of x sub 0? Well, it exists here at this corner. It exists here at this whole jump. It exists everywhere else. It does not exist here, this one point only. So we could say for all x not equal to -4, you could write interval notation, negative infinity to -4, parentheses, -4 to positive infinity. So not including 4. That's another way of writing the same thing. So there you go. All right. Let's see. Problem 19. I gave you guys a little bit of heads up on in the lesson. In fact, I kind of started it for you. It said to use your graphing calculator and make a table. And they told you what values to put in. So we're going to put this in our calculator and then go to the table and see what happens. So we're going to plug, it says 2, 1.5, 1.1, 1.01, 1.001. Then we're going to plug 0, 0.5, 0.9, 0.99, 0.999. Now, these represent the limit as x approaches 1 from the right side, right? And then these represent the limit as x approaches 1 from the left side. So on our calculator, put this in parentheses, x minus 1 divided by parentheses, x to the third minus 1, close, go to the table, type these values in, 2, 1.5, 1.1, 1.01, 1.001. Write these numbers down. 0.14286, 0.21053, 0.30211, 0.33002, 0.33300. Okay, now I think you only put so many values in. 0, we'll try it, 0.5. Yeah, it doesn't let me go past that, so I'm going to just type these in, starting here, 0, 0.5, 0.9, 0.99. Something happened. 0.99, 0.999. Okay, so I'm going to go ahead and type those in. Remember, we can highlight them to see more accuracy. So that's going to be 1. And that's going to be 0.57143, 0.36900, 0.33669, 0.33367. So both of these appear to be going to 1/3. So that's what I'm going to say the answer is, 1/3. Okay? So that's using a table to find a limit. Now it says, confirm your conclusions about the limit by graphing the function over an appropriate interval. Well, let's graph it. We already have it in there. So let's go to window. We're approaching, looks like 1 from both sides. So, I mean, what we could do, we just try it. -5, -5, -5. Just graph real quick. All right. And if you want, you can then do trace and kind of go towards -1 or -1. which looks like it's going to, wait, no, we're going to positive 1. Sorry, positive 1. Positive 1 looks like it's going to about 1/3. So we're going to draw a little quick sketch of this to show we did it. I don't know if I should draw the sketch down here. Maybe I can fit a little more work. So now, is there anything weird happening there? If I go second calc value and I plug 1 in, there's a hole. So there's a hole in the graph. And then it looks like the peak is, I don't know, somewhere around maybe 1 1/3 over here. So the graph kind of looks like this. And there's a hole in the graph right there, but it's around 1/3. Okay. Part B, you got another problem like that. In fact, it's close. It's the limit as x approaches 1 plus, just 1 plus. It's a different equation though. It's x plus 1 over x cubed minus 1. So this is a one-sided limit. And they tell us to put values in 2, 1.5, 1.1, 1.01, 1.001, 1.0001. So we're approaching 1 from the right side. Numbers bigger than 1 getting closer and closer to 1 gradually. So I'm going to go ahead and retype this equation in. X plus 1 divided by x to the third minus 1 table. I'm going to replace these values. 2, 1.5, 1.1, 1.01, 1.00, 1.0001. Those are really big numbers. I mean, looks like it's blowing up, right? I'm gonna write those in real quick. 1.42857, 1.0526, 6.3444, 66.334, 666.33, 6,666.3. So it appears to be going to positive infinity. Technically does not exist. Let's see what the graph looks like. Window. I'll just try that graph. Vertical asymptote, horizontal asymptote. There's a vertical asymptote x equals 1, which makes sense. So the graph looks like that's at 1. And it actually looks like the graph might even cross the horizontal axis and maybe come back down to it. I mean, if you go to infinity, it's definitely going to be, it's going to 0. Positive infinity or negative infinity. So, x from the right side, sure, yeah, vertical asymptote blows up. So that makes sense. Okay, part C, limit as x approaches 1 minus of x plus 1 over x cubed minus 1. So same equation actually. So that'll save us a little time. We already have a picture of the graph, so we don't need to regraph it, right? We just need to type these values in. 0, 0.5, 0.9, 0.99, 0.999, 0.9999. I mean, you probably predict it's going to go to negative infinity, but let's go ahead in 0, 0.5, 0.9, 0.99, 0.999, 0.9999. All right. Well, those exact. Well, those aren't exact. It rounds them and then it doesn't show the decimals. So if you go up here, this does show as exactly 1, a negative 1.714, negative 7.011, negative 67.00, negative 667.0, negative 6,667.0. So it's going to infinity. You know, we would say, yeah, that's going to negative infinity, which makes sense on the picture. So that's how we could use our calculator. And then 2 more problems. Start presenting some just interesting kind of applications or, ways of, using limits to interpret a problem. So 27 says, assume that a particle is accelerated by a constant force. That means it should keep getting faster and faster and faster, like gravity, right? The 2 curves, v equals nt and v equals et, in the accompanying figure provide velocity versus time curves for the particle as predicted by classical physics and by special theory of relativity. The parameter c represents the speed of light. Using the language of limits, describe the differences in the long-term predictions of the 2 theories. Well, let's draw a quick sketch of this. So this is velocity. This is time. And there's the speed of light, which is a velocity. And then they have this line, velocity equals nt, which is classical physics. And that's the idea that, oh, well, if you keep applying a force to something, it'll keep going faster and faster and faster. In this one, is special theory of relativity. And so it says, use language of limits to describe the differences in long-term predictions. So, you could look at this, you say, well, limit as t goes to positive infinity of classical physics is the velocity goes to infinity. And so classical physics says you can keep accelerating. So a force applied to an object causes it to accelerate. If you have no force, then you just maintain your velocity. And then the limit as t goes to positive infinity for et says it approaches this horizontal asymptote c, which is the speed of light. So special theory of relativity says you cannot meet or exceed the speed of light. So as you get faster and faster and faster, as you push the speed of light, you can't get past it. So it's 27. 29 says let capital T equals Ft denote the temperature of a baked potato T minutes after it's been removed from a hot oven. The accompanying figure shows the temperature versus time curve for the potato, where R is the temperature of the room. So we'll do a quick sketch of that. R is the temperature of the room. And then there's this curve here. And that's the temperature of baked potato. Okay. So part A says, what is the physical significance, the limit as t approaches 0 from the right side of f of t? Well, I would say that that answer would be 400 degrees Fahrenheit. And so as you approach 0 from the right, as you go back in time towards time 0, the temperature of the potato approaches 400 degrees as time approaches 0, approaches its initial temperature. Okay, part B says, what's the special significance of the limit as t goes to positive infinity? Well, it goes towards r. As time passes, the temperature of the potato approaches room temperature. Which is how, that's how heat transfer works. It's assuming it's a large room. So as the potato cools off, technically the temperature in the room should heat up a tiny bit. But if it's a big room, it doesn't make that much of a difference that you could tell. In fact, there was a problem very much related with a hot baked potato for response problem a few years ago on the AP exam. People freaked out a bit. They're like, well, we never studied potatoes. It's funny because I probably gave them this problem. But whatever. It was just like a regular calculus problem. They threw a potato into it. Messed with people's heads. That's it.